Okay. There are a few rules that we need to know and understand and apply in all contexts. And these are written at the top of page 20. So a common problem that students face is trying to oxidize or reduce certain things that are always spectators. And they are in this box here. So there's a list of anions that can't be oxidized in aqueous solutions of concentration 1 molar per litre or lower. So that's the nitrate, iron, sulfate, carbonate, phosphate, hydrogen sulfate, hydrogen phosphate ions. Okay, so that's that top list there. And you won't find them on the electrochemical series. Okay, they're not there because they don't react. But there are some ions on your formula sheet that also cannot be reduced in aqueous solution. And this is probably the biggest problem. And that's all reactive metals. Ions. So what am I talking about there? I'm saying that if I have sodium ions in solution, there's no reaction that I can perform that will result in the formation of solid sodium. Why do you think that's the case? If I put a piece of solid sodium in water, what happens?
Explode.
Pretty well, a very violent reaction, isn't there? With our group 1 metals with water. Well, if I can't even put a piece of sodium in water because it will react straight away, how could I possibly form it in water? Because it just won't form. If it's going to react with water, the moment that it comes into contact with water, it cannot form. Okay? The sodium is too reactive. It's too reactive. Okay, because we know that the sodium ion will immediately react with water. Sorry, the sodium metal. So do you see my logic here? That's why if I have the sodium ion in solution, that I'm never going to be able to reduce it in solution. And that goes for all of the metal ions listed in this table. So all of our group 1 metals, plus magnesium, calcium, barium, aluminium ions, and strontium ion. So we've got a couple of our group 2 metals as well. We have to look at our periodic table. We can see where calcium and magnesium are. We're not going to be able to form those ions. We're not going to be able to reduce the ions to form the metal in solution. And we've got aluminium over here as well. And strontium 2+. Now, over here. Okay, so we've got our group 2 metals there, as well as aluminium. I think I've told you this story before, but there was a big dinner when Napoleon invited some important guests along, and kings. He gave them gold plates to eat their meal off, and he ate off an aluminium plate. Because at that time, aluminium was worth far more than gold, because it was so difficult to extract. And so you actually needed add a lot of energy to form or to reduce aluminium ion from aluminium ions to aluminium. And so it was a function of the rarity. So what does this mean? What do these rules mean then? Well, we need to make sure that we don't accidentally react them. Make sure that you're looking and identifying the spectator ions that are present. We sort of talked about that last lesson a bit. And so we want to make sure that we're finding the proper reactants. Look to see if the relevant half equation is on the electrochemical series. And if it is, just copy it straight down. If it isn't, then you're going to use the balancing method that we practiced last lesson, balancing with water, hydrogen ions and electrons. Now, we've got an example which I'll go through in a minute, but I want to perhaps do question 20 on page 21. Now it tells me here I have a copper sulfate solution. And it's asking me about what's going to happen if I store it in a steel container, and most of steel is iron. So iron is the thing that's relevant here, the element that's relevant. It says that the container corrodes, producing Fe2+. So what do we know is happening to the iron container? What's happening to it's being oxidized. So this is an oxidation half, and we know then that we would balance it with 2 electrons. So that's my oxidation half equation. What's the other reaction? What's the other reaction going to be? If this one's oxidation,
the copper would be being reduced.
The copper ions are being reduced. Because the sulfate ion is on our list of spectator ions, isn't it? And it's already it's got as many oxygens as it can handle, basically. The sulfate ion, that's why it's going to be very difficult to oxidize that further. So that makes sense then, but that's my reduction half equation. The sulfate, as I said, it's a spectator. We need to have those spectator ions present though, in order to give us the other reactant, the copper ions. Looking at your electrochemical series, can you see where's the Cu2+ ion and where is Fe solid? Can you see them on your electrochemical series and confirm that they are in this relationship here, where the copper ions is the stronger oxidizer? Because remember that the strength in oxidation is going up on the left-hand side, and that the iron is a stronger reducer. Can you see that that's what the arrangement there? Okay. So it just so happens that for question 20, both of our reagents, or our reactants, were on the electrochemical series, so we didn't have to go through the process of trying to balance out an oxidation or reduction half equation. But if we look at example 1 now, on page 20, we've got copper metal. And it says it's placed in a concentrated nitric acid solution. So we've got nitric acid. This is concentrated. So what we know is that we cannot rely on the electrochemical series to tell us what the product would be. So if it says concentrated, we have to read and find the information in the question that tells us what is our product. It says that we form a brown gas, nitrogen dioxide. Okay, so we're forming nitrogen dioxide. And the solution turns green. Well, copper ions in solution can be blue or green, depending on what it is. So it's telling me then, that's a clue that I formed copper ions. So the common colour of ions, there's another table on the formula sheet that will remind you of the colours of ions. It's earlier on. And that will sometimes be a clue that will help you determine what's happened in a redox reaction. So we haven't formed a precipitate, okay, and there's no solid here. It's the solution that's turning blue or green. All right, now it says write a balanced redox equation. So if I look at this, I can see that it's the nitrate part of the nitric acid that's reacting to form the nitrogen dioxide. Yeah? And so I'm not going to treat it as nitric acid. I'm only going to use the nitrate ion to balance it. Do you remember the rule that we start out with the things that aren't oxygen and hydrogen, and we balance them first? But there's one nitrogen on either side of our arrow, and so that's already balanced. Then we balance our oxygens with water. We have 3 on this side, and we have 2 on this side, so I'm going to need a water. And we balance our hydrogens with the H+ ion, and so 2 H's on that side tell me I need 2 H+ on this side. And finally, we need to balance our charge with electrons. And what I've got here is +2, -1, and on this side, this is equal to 0. So I'm going to need to make this side equal to 0 as well. And I need to subtract another 1, don't I? So that would mean I've got 1 electron on that side. So which half equation have we written? The oxidation or the reduction? Reduction. Because we've got our electron on the left-hand side. So that's our reduction. And we know now we're looking to see, well, an oxidation reaction, and that makes sense that it's the copper, doesn't it? Now, hopefully you can see why it was helpful to just look at the nitrate ion by itself, because this isn't balanced according to this equation here. So that's why this reaction requires concentrated nitric acid, because we need twice as many hydrogen ions as we need nitrate ions for this reaction to proceed. Yeah? Now we look at balancing. So this is oxidation. I'm just going to rub these out. We need to balance our electrons for our full redox. What am I going to do to the top one? Multiply everything by 2 so that we have the same number of electrons. And then this part is the part where students frequently make mistakes, not because you didn't know what you were doing, but because you lost track of your very complex mathematics here. You forgot to multiply something by 2. So these redox equations can get really long. So people who write big often find you don't have enough space. Okay, and now with our full redox, we can have another look and say, do the charges make sense? And yes, they do, because overall on the left-hand side, we've got a charge of +2, and we've got the same on the right-hand side. The charge only coming from the Cu2 plus ion on the product side, and +2 being the result of 4 pluses and 2 negatives on the left-hand side there.